This video is about using polar coordinates to compute double integrals. So we've seen previously that we could use double integrals to find the volume of some underneath some surface. That is, if we think of some function as giving the height above the xy plane, then we could just use a bunch of rectangular prisms and then shrink these things down to infinitesimal base areas to find the precise volume underneath that surface, between that surface and the xy plane. And we've looked at examples and seen sort of different ways of thinking about what's going on with those iterated integrals. So if we had some region, let's look down, straight down at the xy plane, the z-axis coming out toward us. So we're not worried about what the height of the function is, what the function looks like, what that surface is. We're just paying attention to the region that we're integrating over that area on the xy plane. And if we look at that iterated integral, so when we're integrating with respect to x, we're taking from some minimum x value to some maximum x value, and then integrate that with respect to y, adds up all those different strips sort of along the x direction. Or alternatively, for the nice functions that we talked about for which you can reverse that order of integration, integrating first with respect to y gives me from some minimum y value, some maximum y value for some constant x, and then we integrate again with respect to x to add all those up. In either case, what we're looking at is some infinitesimal area. In this case, it's given by dx dy. So dx being the length of that little area, some little sliver of the x-axis, and dy being the width of that little area. And again, we're going to shrink these down to infinitesimal, and so that gives me an infinitesimal piece of the area of the region that we're trying to integrate over. And so then when we integrate whatever function we're integrating over that area, what we're doing is adding up all the values that we get using the height of the function as the height of a rectangular prism, and the incremental tiny piece dA gives the base of each one of those. And so we integrate to add all those up. But the rectangular coordinates aren't always the nicest to work with. So here we have an example. This portion of an annulus, we've got some function. It doesn't actually matter much what the function is, but in this case 2x plus 3y. We want to integrate that function over this annular region. And so I would urge you to pause for a moment and see if you can figure out, just set up this integral. Don't necessarily go about computing it. Just set this integral up. Set up the iterated integral that will give us the volume under the plane z equals 2x plus 3y above the x-axis over this region highlighted here. So it's not particularly nice. It ends up being a bit messy. You have to break it into two pieces, whichever way you slice it, because it's not always one function giving one boundary and the other function giving the other boundary. Things sort of switch up, and you've got to deal with just going as far as one of the coordinate axes, one way or the other, whichever way you choose to do it. So rectangular coordinates here aren't very nice, but seeing something that has this circular piece with the annular region here should make us think of polar coordinates, and that's exactly what's going to help us do a much better job of setting up an integral that's much easier to compute. So let's look at how that's going to work. We need to figure out what our little increment in area, what our infinitesimal little piece of area is, and what we're going to end up with is this little section of an annulus, this little annular region. And so wherever we are in space, that little annular region that we care about is some distance from the origin, so there's some fixed finite value of r there. That's not shrinking down to 0. That's telling us where we are in space for our little annular region. So there's that value of r. But the thickness of our little angular region is dr. That's some infinitesimal little change in r provides the thickness of that little area that we're looking at. And it exists in some infinitesimal little sweep of the angle theta. So d theta tells me what the angle associated with this little bitty piece is. And if you remember, at some point before, you've probably seen that arc length, which here I've written L, if you're measuring your angles in radians, arc length is just the radius times the angle swept out. Now there's another constant involved. It gets more complicated if you're measuring your angle in something other than radians. But if you're measuring angles in radians, arc length is just r times theta. And so what we're looking for is some infinitesimal little change in theta. Then that tells me that that dimension of our little area that we're trying to find, dA, is r d theta. Again, that r is not shrinking down to 0. That r is telling us where we are in space. The d theta is what's indicating that we're talking about a tiny little change in theta that sweeps that out, and then a tiny little dr that gives me the thickness of it. And so what we find is our area element in polar coordinates is actually r dr d theta. And so then if I want to integrate over some region, it's just a matter of adding up the value of the function times one of those little areas. So we integrate across dA and we get the value of the function we're talking about. It might be helpful to remember how to transform from rectangular to polar coordinates. And then let's return to that integral before that was kind of difficult in rectangular coordinates. It wasn't terribly straightforward. But now we should be able to look at this and with what we just talked about in polar coordinates, set up the integral in terms of polar coordinates instead. So do that, and I'll see you in class.